In the last video, I left off on Mercury and lead and their possible electron configurations. And then the focus of this video really is going to be on energy level diagrams, but I'm just going to quickly take up Mercury and lead from last video. So I already wrote it out, but I'll explain it. So when we look for Mercury on the periodic table, it's right over here. So you can see that, well, in the previous row, because we're going to write in an abbreviated notation, unless you want to torture yourself and write out every single one. The noble gas before it in the abbreviated notation we would write is xenon, so we write that. And then we see that, well, in terms of the row, 1, 2, 3, 4, 5, 6, 7, right? So 6. So we would be writing 6s2 because this is the 6s2 part. And then you'll notice there's a 4f, there's an f before the d, and that's because the reason is, so lanthanum is actually, this is a weird periodic table. Lanthanum should actually be here. I think it is, but it's hard to see. Oh, that's not the brightest color. Let's do that in red. So lanthanum is supposed to be here, and then this AC element is supposed to be here. So those are still in the D block, but it's just showing from that to that point. You know, it's these many whatchamacallit, like whatever, elements or whatever. With some weird arrangement. But basically, the reason we didn't do 6s2, 5d1, and then go all the way across the F block and then write, I don't know, 5d whatever, is because that doesn't make sense. We're not going to write 5d again. We'll just keep it as 1. So that's basically how to do it. You would write 6s2, then you notice that, well, it's going to have to go through all these points. So it would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Again, this guy and this guy, these are D block, but the rest of these ones are F block. Not sure what they did here. I should have picked a better periodic table, my bad. Anyways, all right, so you have to go through the entire F block, and then you come back to HF, and then you start counting. Well, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we had 5D1 originally, and then we went to the F block, and then we came back from the F block, and now we end up at 5D9. So we'll just say that's 5D10, and then we're going to put the F block first. So that would be 4F14. That was basically the gist of it. So that's the electron configuration for Mercury. Lead, we see, is right here. So all we can do is just take Mercury's electron configuration and add 6p2. Right? It's the same thing. It's just now it's in the P block, because remember this guy over here, this is the P block. So we just throw it in there, and that's 6p2. And that's really it for those two elements. Weren't too challenging. Well, at least lead wasn't when I gave you Mercury. So yeah, let me just quickly erase this. So let's move on to the next topic, which is energy level diagrams. So there are multiple ways, there are different ways you can represent electron configuration visually aside from writing it out. There's like this one where you might have seen where it goes like this, whatever, and you write a bunch of stuff. You might have seen these boxes where you put in the little arrows. I'm going to show you how to draw energy level diagrams, and the reason is, well, my chemistry teacher focused on it, and it seemed really good to me because it's sort of visually more appealing than doing an orbital box diagram, which is like where you draw a box and be like, okay, 1s, 2s, right? And then you go from left to right, more energy, more E, and then less E. But I like energy level diagrams because you can sort of see that it's like stacking up almost. It's like building the layers. So basically, with that said, depending on the orbital shape quantum number, so we see an S here, S, we see a P, and we see a D. Depending on the orbital shape quantum number, there will be the appropriate amount of orbitals. So if you can recall from that quantum numbers video that was not too long ago, right? This is the S. Oops, this is the S. This is the P. This is the D. This is the F orbital. And you notice that you know, there's numbers associated with it. So there's 1, then there's 1, 2, 3, and this is all orientations. So and that's dictated by ML. The why am I forgetting the number for some reason? Yeah, okay, I don't know. I'm having a brain fart. ML. I forgot it, what it stands for. So much chemistry. But anyways, ML indicates the orientation, right? So L will tell you what is the orbital, and then ML will tell you either like how many and what is the orientation. So that's what's going on here in this little diagram I've drawn. So basically you draw from the lowest energy level to the highest energy level. And again, according to the orbital shape quantum number, you will put the amount of orbitals necessary. So we see in a P, and when you have a P for your orbital shape quantum number, you have 3 spots, because this would be, you know, Px, Py, Pz, right? And then the different orientations go. So we can see that this is like some weird one for the D block, dx squared minus y squared, d, you know, xz, so on, so on. So we include the appropriate amount. So we know S has 1, P has 3 orbitals, D has 5, and F has 7. So if we had an F orbital, let's say 4, like, you know, 4 or whatever F, right? We'd have to draw 1, 2, 3, 4, 5, 6, 7. And in each and every one, depending on how many electrons we have to fill in the electrons like this. We draw the little half arrows. That's basically it. So you just draw from lowest energy level, and you go according to the periodic table. So you know that whole idea, 1s, 2s, you know, 2p, 3s, 3p, 4s, and so on and so forth. And make sure to not forget the rules and principles we talked about in the last video. You know, Hund's rule, the Aufbau principle, the Pauli exclusion principle. We're all going to see that sort of play out here. So let's do a first example. Let's do beryllium. So first thing we do is we write on the side, on the left-hand side, the principal quantum number and the orbital shape quantum number, and then we just draw the orbital. And the orbital is represented by a line. And then we draw the next one, 2s, because it's 1s2, 2s2, and we draw another line. Now we only do one because in the S block, you only have one orbital. And now this exponent will tell us how many electrons to put within that specific orbital. So with 1s, we see there's 2, so we put 1, 2. You have to draw like this half arrow up, half arrow down, because the last quantum number tells you that each electron has its own like different spin. And I'm forgetting which exact rule out of the 3, Hund's, Aufbau, Pauli exclusion, but one of them, I think it's Pauli exclusion, where one has to be up and the other has to be down. Then this is done to minimize electron repulsion. This would be half up, this would be minus half down. And on the 2s, we do the same thing, right? Because there's 2 electrons here and there's 2 electrons here. That's really it. Pretty straightforward. Let's say we did fluorine. We're going to write out all the numbers and letters on the side. 1s, 2s, 2p. So the s's have only 1, but now we're on to 2p. Let me write that better. That does not look like 2p. 2p. 1, 2, 3. Remember what I told you about the p orbital? It's got 3 different orientations, right? So we have to account for that. So in the 1s, well, there's 2 electrons. So we put 1, 2. In the 2s2, there's 2 electrons. We put 1, 2. And then in the 2p5, so in the p orbitals, there's 5. So don't make this mistake where you do like this, this, and this. I'm done. No, wrong. Not what you're supposed to do. You're not following Hund's rule. You fill them out one at a time. So 1, 2, 3, 4, 5. And you may be like, well, I just did the same thing, right? I just wrote this, 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 this. Why isn't that correct? When you get to certain situations where, let's say, I don't know, let's say you had 3 orbitals and 3 electrons, and you did this when you were supposed to do this. So this is correct, this is wrong. That's how you get confused. So just as a rule of thumb, always, even though you know you have enough electrons to, you know, do the dumb way, I'll call this, aka wrong, right? When you do it like that, you'll confuse yourself in other situations where you have to disperse it equally. So keep that in mind, all right? This is right. When you space it out, this is wrong. This is just a hypothetical situation I laid out. Because you may be wondering, okay, if I just wrote it like this, What's the big deal? What's the fuss, right? But I'm telling you, you'll do it by accident on a test and you'll lose a mark and you'll be like, damn, Gerda was right. And I'll be like, I told you so. So yeah, don't do that. Okay, let's move on to the next one. Sulfur. We're going to write it all out. 1s, 2s, 2p, 3s, 3p. 1s, 2s, 2p has 3 orbitals, 3s, the s will only have 1, and then a p has 3. Started off with 1s, bang, bang, 2 electrons, and 2s, 2p6, right? Just, again, just make it a habit so that you enforce the idea in your mind. 3s, 3p, 1, 2, 3, 4. That's how you do it. Again, following Hund's rule, fill it out one at a time. And yeah, that's pretty much it. That one was pretty straightforward as well. We're just getting more and more. So again, you know, bottom, low energy. I'll call it low E, and then you go up to high E. All right, let's do a more fun one. 1s, 2s, 2p, 3p, 4s, 3d, 3p, nope, I made a mistake. 1s, 2s, 2p, 3s, 3p, 4s, 3d. Okay, 3s, 1, 2, 3, 4s. Okay, now we're in the d orbital. So there's 1, 2, 3, 4, 5. And I'm just going to erase the stuff up here. We got some more space to work with. So 1s, 2s, 2p, 3s, 3p, 4s, 3d. Yikes. Okay, but we can do this, don't worry. 1s, there's 2 electrons. In 2s, there's 2 electrons. In 2p, there's 6 electrons. Again, reinforce the idea in your brain. This is the way you do it, even though it doesn't matter if you did the other way, but just don't do it. 3s, 3p. Oh my god, I'm not following my own word. I'm a hypocrite. Yikes, and I can't draw as well. Right? Because there's 6 in 3p. 4s, there's 2. Now 3d, there's just 1. Now, you may be wondering, or maybe not, how come the 3d is above the 4s? Doesn't the 4s have more energy? And that's incorrect. The 3d orbital has more energy than the 4s. I think I mentioned in the last video as to why when we write the electron configuration for scandium, you do 4, like, you know, it says blah, 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 and then you do 4s, and then you do 3d. Some things, or actually a lot of things, will show you to write it in like numerical order. You'll put the 3d before the 4s, but I think that just confuses people, to be honest. It confused me, and then my teacher was like, no, don't do that, right? Because technically 3d has more energy than 4s, so it should be here, really. So yeah, that's basically it. I have one more, a challenging one. Let's say I asked you to do, you know, uranium, because, you know, I like torturing you because uranium is right over here. Now, I learned this in my chemistry class, and I'm not sure if this is the, like, I'm not sure if this is technically the correct convention. I think for energy level diagrams, you can't do an abbreviated version. You would have to write out every single energy level, and I think that's not really practical. Not even on a test you're going to be asked that, really, at least in grade 12 chemistry. So if you do get asked, hopefully your teacher is chill and will accept this. So you can write the abbreviated notation, and then you can put the rest. So 7s, 6d, 5f. So hopefully your teacher's chill with that. Again, not sure if this is 100% correct. I'll just put a big question mark here. Like, maybe? I'm just teaching this to you anyways, because, like, I'm not sure if it's the exact correct convention, but it's like, there's nothing really wrong with it. You're still stating the same thing. It would just be a, you know, a big pain to write, starting all the way from, you know, the first row and you make your all the way down to uranium. It just doesn't make sense. But anyways, so let's say we did for 7s, the electron configuration, the energy level diagram. 7s just has 1. And then 6d, there's 5. 1, 2, 3, 4, 5. And then the F1's got 7. 1, 2, 3, 4, 5, 6, 7. Okay, in 7s, you put 2 because the exponents here is 2. In 6d, it is just 1. And then F, there's 3. 1, 2, 3. And that's, basically, it. There's nothing really else to energy level diagrams. It's just that you represent these electrons in this way with, from the bottom to the top. It's like building a little building. You establish the foundation and you keep going on and on. So I taught you a little, trick maybe, where you can throw an abbreviated notation into energy level diagrams. Again, I'll repeat it. I'm not sure if it's 100% the correct convention. It might be, I'm not sure, but I just think it's like a nice useful way to sometimes imagine certain electron configurations, because when you write it out it can get really messy, but I think drawing like this sort of helps to understand a little bit more. But yeah, that's pretty much it.